Okay, salt solution. We've already talked about the fact that salts can affect the pH of a solution when an acid-base neutralization occurs. We're going to talk today about the idea of just taking a salt and dissolving it in water. What kind of solution will we get? Will the solution be neutral? Will the solution be acidic? Will it be basic? Some salts, as we learned previously, can produce acidic solutions, can produce basic solutions. So we'll take a look at how we can categorize those different types of salts, and then how we can actually calculate the pH of a salt solution. So salts that produce neutral solutions. Salts that produce neutral solutions are salts that contain a cation, a conjugate acid, that's from a strong base, and an anion, a conjugate base, that's from a strong acid. How do we define a strong base? Hydroxide-containing compounds. So in a hydroxide-containing compound, what types of cations did we see? So sodium hydroxide, for example, is a hydroxide-containing compound. Potassium hydroxide, metals, and often group 1 metals. So the cations that we're going to see, if they're from strong bases, are going to be metal cations. Often we will see group 1 metal ions. What were the 4 strong acids? Hydrochloric, perchloric, sulfuric, and nitric. Okay, so what kind of negative ions are we talking about then? What are the negative ions that are in those 4 acids? What's the negative ion in hydrochloric acid? The chloride ion, Cl minus. What is the negative ion in perchloric acid? ClO4, the perchlorate ion. What's the negative ion in sulfuric acid? Sulfate, SO4 minus 2. The negative ion in nitric acid? Nitrate, NO3 minus 1. So if we see a salt that is a metal ion paired with one of these negative ions, that salt will produce a neutral solution. So an example, sodium chloride or potassium chlorate. A metal paired with one of those 4 negative ions. Questions? All right, let's take a look at salts that produce basic solutions. These will be salts that contain a cation, which is a conjugate acid, from a strong base and an anion, which is a conjugate base, from a weak acid. So cations from a strong base. Again, we're talking about metal ions. Typically, we'll see group 1 metal ions. What about the anions? What kind of anions would we see? Any other negative ions with the exception of the 4 listed above. So any other negative ions except the 4 above. So examples, something like sodium fluoride. We've got the metal ion and we have a negative ion that is not from a strong acid. Something like potassium acetate. We have a metal ion, we have a negative ion that is not one of the 4 listed above. All right, and then last, salts that produce acidic solutions. These will be salts that contain cation, which is a conjugate acid, from a weak base and an anion, which is a conjugate base from a strong acid. So the types of cations that we're going to see are going to be from weak bases. Weak bases are not hydroxide-containing compounds. They're substances that accept a hydrogen ion when they're put into water. So we're going to see things like the ammonium ion. The ammonium ion is from ammonia, a weak base, after it's accepted a hydrogen ion. We said that common weak bases are amines, which are essentially hydrocarbons with nitrogen in them. We'll see then hydrocarbons with nitrogen having an extra hydrogen with a positive charge. X and Y are just any number of carbons, any number of hydrogens. And the anions, well, we'll see the chloride ion, the perchlorate ion, the sulfate ion, or the nitrate ion. So an example, ammonium chloride would be an example. So there's two things that you'll have to do with salt solutions. One, you'll have to be able to identify if a salt solution will be an acidic, basic, or neutral solution, depending on the type of salt that's dissolved in the solution. And you're going to have to calculate the pH of the solution. So let's take a look at a problem where we do that. Okay, so our problem says identify the following salt solutions as acidic, basic, or neutral and calculate the pH. So let's start with the first portion of the question. Let's start by identifying the salt solutions as acidic, basic, or neutral. Now, in order to identify whether the salt will produce a solution that's acidic, basic, or neutral, we need to look at the cation and the anion and decide which of the above categories that salt fits in. Sodium fluoride. What category does that fit in according to the definitions we just took? Ben? This solution will be a basic solution. When we calculate its pH, then we should expect to see what kind of pH for a sodium fluoride solution. pH that's greater than 7. We'll actually calculate it here in just a minute, but let's finish going through and identifying what types of solutions that we'll have. For B, we have potassium perchlorate. What kind of solution would that be? Neutral solution. Well, then we don't even need to worry about calculating the pH here. The pH should be what for neutral solution? 7. And according to the number of significant figures in our concentration here, how many decimal places would I put after the 7? 2. So 7.00. So we are completely done with B. We've identified it as a neutral solution and we've calculated or found its pH. How about C? To be an acidic solution. And we should expect to see a pH that's where on the scale? Less than 7. Okay, so I'm going to actually need to calculate what the pH is for A and for C, but I have an idea of where that pH should be when I make that calculation, which is a good point. It's a good reference point. Let's take a look first at A. We have a 0.30 molar sodium fluoride solution. So I take enough sodium fluoride, dissolve it in water, to make a 0.30 molar solution. Once I dissolve the sodium fluoride in water, what do I really have in water at that point? It's an ionic compound. So you have ions. What ions do I have? Sodium ions, and I have fluoride ions. So I have a solution of sodium ions and fluoride ions. The sodium comes from a strong base. So what type of conjugate acid is it? Is it strong or weak? The weak conjugate acid. If it's a weak conjugate acid, will it react with the water at all? No. So the sodium will not affect the pH of the solution, so we'll ignore it in our calculation. The fluoride ion, however, comes from a weak acid, which makes it what kind of conjugate base? A stronger conjugate base, so it will have an effect on the pH of the solution. Let's look at how. If I have the fluoride ion in water, and this is acting as a base. Bases accept hydrogen ions, so this is going to accept a hydrogen ion from the water, forming HF and OH minus. Now we said that this solution was going to be a basic solution, and the presence of the hydroxide ion is why this solution is a basic solution. So to calculate the pH, we need to know how much hydroxide ion is produced when the sodium fluoride reacts with the water. Well, I could do this with an ice table. If I have 0.30 molar sodium fluoride, that means I have 0.30 moles in every 1 liter. When this breaks up, it will break up into sodium ions and fluoride ions in a 1-to-1 ratio. So for every 0.03 moles of this that break up, I would also get 0.03 moles of this and 0.03 moles of this in the same volume of solution. Because this is a 1-to-1 ratio, then I would have 0.30 molar sodium ions and 0.30 molar fluoride ions in the solution, which means my initial concentration of fluoride ions is 0.30 molar. Don't care about the water. These would be 0. This will decrease by some value x. These will increase by some value x. At equilibrium, I'll have 0.30 minus x, x, and x. Now I could write a Kb expression because this is a base. Kb will be equal to the concentration of HF times the concentration of OH minus divided by the concentration of F minus. If I knew Kb, I could plug in that number there, and then I could plug in these here, solve for X, and I would know the hydroxide ion concentration. Well, I don't know Kb, but I do know Ka for HF. What was Ka for HF? 7.2 times 10 to the negative 4th. And what is true about the Ka for an acid and the Kb for its conjugate base? How are they related? Morgan? Yeah, Ka for an acid times Kb for the conjugate base are equal to 1 times 10 to the minus 14th. So I can plug in Ka here for this acid and find Kb for this conjugate base. Then I have a value to plug in there. So Kb is equal to, I got 1.3888 repeated, so give myself 4 or 5 decimal places, times 10 to the minus 11th. All right, so 1.38889 times 10 to the minus 11 is equal to x times x divided by, because this value is very, very small, what assumption can we make about this x here? Like subtracting 0, that will make our calculation a little bit easier. So divided by 0.30. So multiply both sides by 0.30 and then square root to solve for x. X is equal to what? Take out your calculator. what's x? 2.04124 times 10 to the negative 6. Okay, so that is the concentration of the hydroxide ion. We can use that then to find pH. We can first find POH, and then we can find pH. And I'm wondering when you guys are going to stop me from doing all the extra work that I do. No, because there's not an acid. Well, actually, yeah. Because you'll have a small amount of acid, but then you still have to do a lot of the work. More work than you have to do. Isn't this a weak base, guys? And aren't we looking for the hydroxide ion concentration? For a weak base, what's true about the hydroxide ion concentration? Isn't that the math that we literally just did? Isn't this the concentration of the base? Didn't you multiply that by Kb? And then didn't you take the square root? You don't need to set up that ice table to do that calculation. If you recognize that you have a weak base or a weak acid, you can use these equations as shortcuts to eliminate some of your work. Now you can go through and do all that work. Doesn't make a difference. It's just a time saver for you guys when you're doing your homework, when you're doing your tests. Morgan? No, nope. Either way works, and I don't care if it makes sense to you to do an ice table and to figure it out like that, that's perfectly fine. Keep doing an ice table. If you want to just plug it into an equation, great, that works as well. Either way, we're going to get x is 2.04 times 10 to the minus 6. We can find the POH then. POH is equal to the negative log of the hydroxide ion concentration, so we can plug that in there, and then we can calculate from the POH the pH. I got 8.31 when I did that calculation. Does that answer make sense? Yes, it's greater than 7 like we predicted. We know that the solution should be basic because we have a salt that should produce a basic solution. All right, so let's do C. Let's see if we can use that shortcut. If you don't want to use that shortcut, you can go ahead and set up an ice table and go through the math that way. I'm going to show you guys how to just start with that shortcut, okay? So in C, we have a 0.30 molar solution of ammonium nitrate. The ammonium ion comes from ammonia. Ammonia is a weak base, so what kind of conjugate acid is the ammonium ion? Strong, so it will have the ability to affect the pH. Will the nitrate ion have the ability to affect the pH? No, it comes from a strong acid, so it's a weak conjugate base, so it does not affect the pH. So we'll have the ammonium ion reacting with water in solution. It's acting as an acid. Acids donate hydrogen ions, so we'll get ammonia and what? H3O plus the hydronium ion, which is why the solution is an acidic solution. We have the hydronium ion being produced. Well, we need to know the hydronium ion concentration then to find the pH because this is what affects the pH of the solution. That's equal to the square root of the concentration of the acid times Ka. Well, what is the concentration of the acid? The acid is the ammonium ion. 0.30 molar because this breaks up in a 1-to-1 ratio. So the hydronium ion concentration is equal to the square root of 0.30 molar times Ka. Well, I have Kb for this as a base, for ammonia as a base. I can use that to find Ka for the conjugate acid. Ka times Kb is equal to 1 times 10 to the minus 14th. Kb for ammonia is 1.8 times 10 to the minus 5th, I believe. Is that right? Yep. We can plug that in and find Ka. I think it's 5.55556 times 10 to the minus 10th. So 5.55556 times 10 to the minus 10th. And that will give us the hydronium ion concentration, which I calculated to be 1.29099 times 10 to the minus 5th. Thank you. Now, once I know the hydronium ion concentration, how do I find pH? The negative log. So I take the negative log of this value here, which will give me the pH. And when I calculated that, I got 4.89. Does that value make sense? Because it should be less than 7. It should be an acidic solution. Now, the last thing I want to show you before I let you guys have some work time is I want to propose a question to you. And I won't ever ask you to do calculations relating to this, but I might ask you to qualify a solution as acidic, basic, or neutral. What if the salt comes from a weak base and a weak acid? What if we have a salt like ammonium cyanide? We have a cation from a weak base and an anion from a weak acid. This is a stronger conjugate acid. This is a stronger conjugate base. What is the solution going to be? Well, it depends on whether this is a stronger conjugate acid than this, a conjugate base, or if this is a stronger conjugate base than this, a conjugate acid. So which one of these is a more powerful conjugate acid or base? Remember, Ka and Kb tell us how strong an acid or a base is. So if I could figure out the Ka for the ammonium ion and the Kb for the cyanide ion, I could compare, is this bigger than this, or is this bigger than this? Which is bigger? And that will tell me then which is going to, whether the solution is going to be acidic or basic, which one of these is going to be able to dominate then in that solution. Well, it's easy to look up a Kb for NH3 because NH3 is a common base. Excuse me, 1.8 times 10 to the minus 5th. And it's easy to look up a Ka for HCN because that's a common acid, and that is 6.2 times 10 to the minus 10th. How can I find a Ka then for NH4 and a Kb for Cn minus? Set up, as Ben was, I think, about to say, set up that equation, Ka times Kb is equal to 1 times 10 to the minus 14th, and solve. So to find Ka for the ammonium ion, Ka times 1.8 times 10 to the minus 5th is equal to 1 times 10 to the minus 14th. Kb, and we actually just solved that above, or excuse me, Ka is 5.55556 times 10 to the minus 10th. To find Kb for Cn minus, 6.2 times 10 to the minus 10th times Kb is 1 times 10 to the minus 14th. And Kb for Cn minus is 1 point what? 6128 times 10 to the, that seems really big. 1e, negative 14. Make sure you're using your E key. Do not use times 10 caret. Your calculator can't discern the order of operation for negative fifth. So, is this a better base or is this a better acid in comparing those two numbers? So this is a better base and this is an acid. So what will the solution be? Basic. Now I won't actually ask you to calculate the pH because you would have to look at some of those factors, but you might have to be able to identify whether a solution is acidic, basic, or neutral, depending on whether the Ka or Kb is stronger. Questions, comments, concerns? Okay, you guys have just under 20 minutes of work time.